Hello, students. Turns out Mrs. Boyce has COVID. Yay, so fun. So we're going to go ahead and do a video for the 4.4 notes. And if any of you are wondering, we will do the quiz when I return after fall break. So for you guys, that'll be on Tuesday, the 25th of October. I apologize that that's going to be how it's going to have to be. It will still only be on 4.1 through the first half of 4.3. But realize we will be doing the 4.5 notes that day, so try not to get too far behind on homework or anything. So let's go ahead and jump in. The first thing we're going to talk about is domain of logarithmic functions. Here are your learning objectives. Okay, so the thing about logarithms is that you cannot take a negative logarithm. Okay, so it says it right here. Recall, logarithms are only defined for positive numbers. Okay, so what that means is if we're going to plug something in here, then we cannot let the whole thing, so we'd plug in for x, but then this whole thing cannot be negative because logs of negative numbers cannot happen. It's kind of like how we can't take an even root of a negative without getting i's. Same thing, they're just not defined, and it's because the graph looks like this, right? So there's no way to get a log over here. Okay, so the first thing I'm going to do is I'm going to flip my x and my 2 around because I just don't like the way that that is. So that's the first thing I'm going to do. Okay, and you can actually use transformations to help you on this one. So we'd have to factor out the negative, remember, because our a value has to be 1 to use transformations. Okay, but what this is saying is that this right here is a reflection. It's inside the function, so this is going to be a reflection across y. And this one tells me that we are going to shift it right 2. Okay. So if you're thinking about the graph, this is what the graph normally looks like. Right? So if we're going to shift it across the y-axis, okay, so if we're going to go across y, then it's going to look something like this. And then if we shift it right 2, it's going to end up more like this. Okay. And remember, there would be an asymptote. In the original, the asymptote would be across here. Okay. But when we shift it right 2, our asymptote comes with us. So our asymptote also shifts right 2. So the equation of the asymptote is that x equals 2. So the domain of this one would be anything from negative infinity all the way up until 2. Okay. You can also do this algebraically. Okay. So if you have 2 minus x, this quantity needs to be greater than 0, because we can't take a natural log of 0, and we can't take a natural log of a negative. So then we would have negative x is greater than negative 2. We divide by our negative 1. And remember, when we divide by negatives, we would have to flip our sign around. So x needs to be less than 2. Well, that's the same thing as this. So both ways it came out the same. So there's kind of 2 ways you can think about it. All right. For B, we have this. So the first thing I would do here is factor. Okay, so this is going to be the log of x squared. Let's see, so that would be x plus 3 times x plus 6. Okay, and again, we need this inside to be greater than 0. Okay, well, how we solve inequalities is with number lines and checking our values, right? So we would have to do x plus 3 equals 0 to get this critical point, x plus 6 equal to 0 to get that critical point. So our critical points are at negative 3 and negative 6. So I'm going to put negative 6 here, negative 3 here. Okay. So let's do like f of -7. Okay. So that would be -7 squared plus 9 times -7 plus 18. And then we'd have to put that in our calculators. Let me go ahead and get mine out here. So -7 squared, make sure you have parentheses around that one, plus 9 times -7 plus 18. So that's 4. And the question is 4 greater than 0? Can we plug a 4 in here and take the log of it? And the answer is yes. You can take a log of 4. That's fine. So that one works. And then here we can test like f of -5, which would equal basically the same thing here. -5 squared plus 9 times -5 plus 18. So over here I'm actually going to take this and I'm just going to go back in and get rid of my 7s and add a 5 instead. Because that'll make my life easier. Maybe, if I can get it to go where I want it to. Okay, so that one's -2. So this is saying, can we take the log of -2? We cannot. That one will not work. We do it for the same thing over here. We're going to do f of 0, because 0 is easy, right? It's going to be 0 plus 0 plus 18. So can we take a log of 18? Yes, we can. That's fine. So our domain for this one is anything between -6 and -3. That's where we are able to take that logarithm. Okay. Ooh, here's another tricky one. So the first thing I would do on this one is I would combine your logs. They have the same base, so you can combine them because of this. This negative tells us that we can use the difference property. Okay. So we would do 6 minus x on top and x minus 2 on bottom. Okay. Now, this became a rational function. Okay, this is a rational function. So how do we figure out, again, we need the inside to be greater than 0. So how do we solve rational inequalities? This is something we've done in the past. So we need to get our critical points. Okay, critical points for these come from x-intercepts, or the top, and vertical asymptotes, or the bottom. Okay, so we're going to set 6 minus x equal to 0. So that would be -x equals -6, x equals +6. So that's one of our critical points. Okay, and then we would also do x minus 2 equal to 0, and get x equals 2 is another critical point. Okay, so we're going to check critical points of 2 and 6. So we'll start with f of 0, would be 6 minus 0 over 0 minus 2, which would be 6 over -2, which would be -3. And can we take the natural log of -3? No. Then we can try like f of 3 here would be 6 minus 3 over 3 minus 2. So that would be 3 over 1. Can we take a natural log of 3? Sure. And then we do it for this one over here. And we say, I don't know, how about f of 7? That would be 6 minus 7 is -1 over 5. Can we take the natural log of -1/5? No, we cannot. So the domain for this one would be between 2 and 6. And these would actually both be parentheses. The 2 is because it's a vertical asymptote, so that's never going to happen anyway. And with the 6, what happens if you put it in a 6 here is you get the natural log of 0 over 4. But if you try and do a natural log of 0, it's going to tell you that that's not a number, okay? Because it's not. It is not defined. So these should both be parentheses. It does not include them, okay? So there's some answers for you on our domains. and a couple different ways of kind of going about how to solve them. So hopefully that was helpful for you. So all of that being said, now we still need to be able to do these graphs. So the reason that this is helpful would be that we need to know our domain in order to graph. Okay, so the very first step in graphing logarithms is to find the domain. So remember, we can't take a log of a negative number. So negative x has to be greater than 0, which means that x has to be less than 0, because we would divide away our negative 1, and that would give us positive x. We have to flip the sign because we divided by a negative 0. So x has to be less than 0, so our domain is anything from negative infinity up to 0, not including 0, because we can't take logs of zeros either. Okay. All right. And then our range on a normal logarithm function is not restricted, right? This would be our axis. So it's not restricted at all. So our range, in theory, is all real numbers. We do have a vertical asymptote at x equals 0 most of the time. We do need to double check and make sure that that hasn't been shifted at all. And then we would look for x and y intercepts. So x-intercepts are where y equals 0, so it would be where 0 equals log base of 1/4 of negative x. And then we would have to solve that. So I'm going to take 1/4 to the 0 power and 1/4 to the log base 1/4 of negative x power. So anything to a 0 power is 1. This part's going to cancel, and we're going to get negative x. So that tells us that our x-intercept is at x equals negative 1, 0. Okay. I'll go ahead and put this in a color for you guys. Okay. Okay. So our vertical asymptote is at x equals 0, right there. Okay. Our x-intercept then is at negative 1, 0, so it's right here. Okay, now our y-intercepts would be where x is 0, so this would be the log base 1/4 of negative 0. Hi, Lolo, can you go get Daddy, please? Equal to y, and again, we can't take a log of 0, okay? So there is no y-intercept, and that makes sense because of the asymptote. At x equals 0, okay? All right.
Mommy, I want cuddle your food.
Can you go get Daddy, please? Mommy's working. Sorry, guys. Okay. So this is still really hard to tell what the heck is going on. So we're going to talk about transformations with this one also. So if you look here, remember what happens with a log base of a fraction. So if we look back at our notes for a log base with a fraction in it, it looked like this. Okay. So this 1/4 essentially reflected the log. So it normally, a log would look like this. But because it's a log base 1/4, it's kind of already a reflection. So you can think about it as if it were a base bigger than 1, it would look like this. But this is actually log base of 4 to the negative 1 of x. So that negative 1 actually reflects. Okay, so let's go ahead and go back to the one we were working with. Okay. So we were thinking that it should be like this because it's a log. But then we're realizing that this is the same as log base 4 to the negative 1 of negative x. And you can think about it like taking it the 4th to the negative 1 power of that, and it cancels out, and that equals negative x. But then on the other side, we would have had the reverse, etc., etc., okay? So what it does is it flips it this way. Okay? So let's go ahead, here I'll put what we were expecting in black for you guys. So this is what we would have expected, and it should go through that point. Sorry, I'm a bad artist apparently. And then it would have reflected. Okay, so it would have looked like this, just by being log base 1/4. But then, this negative is also a reflection, but this one is going to be a reflection across y now. So ultimately, our log is going to look like that. Okay. And we could get a little bit more specific if we wanted to. We could plug in some values and get some better points. For this example, I think that's enough. But I just want you to realize it's because this is a double reflection that it looks like this. Because if we had just gone in thinking it was just this one reflection, we would have said, okay, looks like this, reflect across y, looks like this. But what the heck, ours actually ended up looking like this. What's going on? And it's because of this 1/4 right here. So I just want to make sure you guys understand that. The parent function here is a little bit funky. All right. So let's go ahead and move to the next one. Okay, same process here. Let's try this one using just transformations and see how this one goes for us. So the transformations here that I'm seeing, well, first of all, we got to factor out our negative. So we've got log base 2 of a negative x minus 4. So this one here, this minus 4, tells us that we're going to go right 4. And this negative here tells us we're going to reflect across y. Okay, and our parent function here is log base 2 of x. Now remember, logs with bases bigger than 1 just look like that. Okay, so then our domain normally would be restricted from 0 to infinity. But because we shifted it right 4, this is going to be 4 to infinity. Okay. And again, that's because our vertical asymptote would have started at 0, but it shifts over with us. So our vertical asymptote is actually at x equals 4. So we go right there. There it is. Okay. Now the range normally is not restricted. Okay. There's no reason for it to be restricted. So your range is still just all real numbers. All right. So again, normally we would have expected it to look something like this, but we know it's going to reflect across y, so we know it's going to look something like this. Okay. Now remember, a normal x-intercept on a logarithm function would be at 1, 0. There's always a point right here at 1, 0. But we have to do all of these transformations also to this point. So this point is going to get reflected across y, which would put it right here. And then it's going to get moved right 4. So 1, 2, 3, 4, it ends up right here. Okay. So it's kind of a weird thing that happens to it. Now, in this case, it does stay our y-intercept, or sorry, our x-intercept, but that's actually kind of weird that it goes through transformations and still ends up as our x-intercept, to be perfectly honest with you. Most of the time it moves. But in this case, we don't even have to do any math necessarily. We know that this is going to be at 3, 0. Now, our y-intercept is a little trickier. We don't necessarily know what that was going to be. So we do still need to come in and plug 0 in for x and go ahead and solve it. So this is log base 2 of 4, which is equivalent to log of 4 divided by the log of 2. So we'll go ahead and get our calculator back here. So log 4 divided by log 2 is 2, which makes sense, right? 2 to what power is 4? 2 squared, okay? So that means that our y-intercept then is at 0, 2. So we'll go ahead and put that point on. Let's pick a color for that one too. Let's go orange. Okay. So we're going to go ahead and put that one there. Alright. So now, remember the ones we're actually working with are this pink one and this orange one. So we knew the parent function started like that, and then we knew that it got reflected across y, which would make us think it's going to look like this. And then it got shifted right 4. So same shape, just shifted a little bit. And that actually does make perfect sense with this, because we're going to go over here, cut across this one, hit this one, and then that's going to go on forever also. And there we have it. And we did this one almost entirely with transformations. So that's another option of how to do these also. So follow up, determine when f of x is greater than or equal to 0. So what this is asking you is, when is this above the x-axis? What x values is that true for? And that is from negative infinity all the way up until that x-intercept at 3. And in fact, it's equal to 0 there. So you can go ahead and bracket that one. Okay? All right. Let's do another one. Actually, I'm going to let you guys try and work this one out on your own. I will post the completed answer, but I want you to try and work it out on your own. Okay. All right. So we're going to do some working with logs like we were working with exponentials, where we need to actually go ahead and solve them analytically. So the first thing I'm noticing here is that we have a base 9 and a base 9. So the very first move I'm going to make is I'm going to take 9 to the power of both sides. Okay, so what's going to happen is that's going to go away. Hold on. I lied, you can't do that yet. You have to do one thing first. You gotta take this guy out. So this is actually 4 log base 9 of x to the, of just x now, is equal to log base 9 of x. Whew! Okay. So what are you guys noticing here? What is unique or special about this? Hopefully you guys, I've given you enough time to think about this. Okay. So, for what x's would these be equal? So this one's kind of weird. So I'm going to give you another thought process for this. Okay? But for the record, you could still take 9 to the power of both of these. Okay? You could. The problem here is that this doesn't cancel quite the same because of this 4. Okay? So I don't know how much good it does you. So let's think about it a different way. Let's realize that if you have log base 9 and log base 9, and they're equal to each other, then that means that this part needs to be equal to this part. Right? Those have to be equal in order for the wholes to be equal. So then something we can take x and minus it over to the other side. So we have x to the fourth minus x equal to 0. And we can factor out an x. And then this actually factors. That's a difference of cubes. So the difference of cubes factors to the cubed root of the first one minus the cubed root of the second one times by the cube root squared of the first one plus the cube root of the first one times the cube root of the second one, which will be plus x. And then the cube root of the first one squared, which gives you plus 1. Okay, that's a formula. You guys can look that up. It's called the difference of cubes. Okay. So this gives us various scenarios here. So either x can equal 0, x minus 1 can equal 0, or x squared plus x plus 1 can equal 0, and it would make this whole 0. So these ones are pretty boring. Okay. This one just gets, I'm just going to even slide this on over here. Okay. X equals 0, x minus 1 equals 0 just gives you that x equals 1. So there's kind of the two options. And then this is the more interesting one. Okay, so we can try to factor this. Doesn't work. But we can take the quadratic formula. So x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So really quickly, we should notice something. This is going to be 1 minus 4, which is a negative under an even root. This is a non-real answer, and we don't need to worry about it. So so that's essentially an extraneous solution. So the two solutions that we could use, though, are x equals 0 and x equals 1. And I'm going to be honest, guys, if you thought about that very hard, you probably figured that out anyway. Because for what numbers are itself to the fourth and itself the same? The only answers are 0 and 1. Because 0 to the fourth is still going to be 0, and 1 to the fourth is still going to be 1. But anything else to the fourth power is not going to give you itself back. Those are the only ones. Okay? So there you go. Let's try this one out. The very first thing I notice is that that's a negative. I don't like it. Makes me uncomfortable. I'm going to get rid of it. So then we have the log of x equal to negative 8.5. And realize that this is a base 10 log, right? So let's go ahead and take 10 to the power of log of x and set that equal to 10 to the negative 8.5. Now this part's going to cancel. We're going to be left with x equals 10 to the negative 8.5. Which is equal to 1 over 10 to the positive 8.5, which is equal to 1 over a very big number, which is approximately 0. So you can actually do this in a calculator, but realize that that's e negative 0.9. So that means you need to move your decimal point to the left 9 places. So that would be point 1, 2, 3, 4, 5, 6, 7, 8, 9, 3. Which is basically 0. Okay. But then that's interesting. Because what happens when you try to take the negative log of almost 0? Interesting. That's exactly what it came out as. Okay. go ahead and move on. Okay, so on this one, I'm noticing first of all that there's two logs, and there's a subtraction sign in between them. This tells me right away I want to use the difference property. So we're going to have the log of x plus 5 over x plus 2 equal to 2. It's the first thing I'm going to do. Now, this is a log base 10. So I'm going to take 10 to the power of the log of x plus 5 over x plus 2 equal to 10 to the second power. This part's going to cancel. You're going to be left with x plus 5 over x plus 2 equals 100. Okay. Now from here, you guys know how to do this. You really do, I promise. You're going to multiply by the denominator to get it out of the denominator. So you'll have x plus 5 equals 100 x's plus 200. Then you got to get your x's together. You got to get everything that's not an x away from it. So x minus 100 x's is negative 99x. And that's going to be equal to 195. So then x is equal to whatever 195 divided by a negative 99 is. So apparently that reduces just a little bit to negative 65 over 33. Or approximately negative 1.97. Because it's actually 1.96 and the 9 and 6 both repeat. Which is awful close to negative 2. So let's try this out. The log of 2 plus 5, I'm rounding, I realize that, minus the log of 2 plus 2, hopefully equals 2 or close to it. I am rounding quite a bit, so this is probably not going to come out perfectly. So something went wrong. So let's go back and look and see. Oh, that's what I did. This should be a negative 2. Okay. So this essentially comes to about the log of 3 minus the log of 0, which doesn't actually exist. Hopefully is equal to 2 or close to it. Uh-oh. Uh-oh. What's happening? Okay. So we need to go back and look, and we need to double check for mistakes. This may be an extraneous solution. Okay. So let's check without any rounding is the first thing I'm going to do. Let's not round at all. So let's say the log of negative 65 over 33 plus 5 minus the log of negative 65 over 33 plus 2, and see what that does. Hey, look at that. So let's double check. I'm guessing I just messed up a sign somewhere. So this is the log of 3.03 repeating minus the log of So we're going to think about what would happen if you put this back into this form. right? So now if we take this number, divide it by that number, what do we get? Interesting. Think about what this means. Log base 10. That means that 10 squared equals 100. Is that true? Sure is. Okay. So there we go. Without any rounding, it worked out just like we thought it would. Okay. Okay. So we're going to do a similar thing over here. We're going to simplify first. So we've got the log of x plus 4 equal to the log of 4x. Now, and that's because of the sum property. Okay. So the first thing I'm going to look at here, once I have this, is that this and this have to be equal. They both are inside of the same log with the same base. So x plus 4 has to equal 4x, which means that 4 has to equal 3x, which means that x has to equal 4/3. And that one really is that simple. But you should always double check and make sure nothing's extraneous. So we've got log of 4/3 plus 4 equal to the log of 4/3 plus the log of 4. Okay, so we've got that decimal, it's like 0.727. We've also got the log of 4/3 plus the log of 4. Hey, look at that. Okay, so this is interesting because of what it implies about this. So if this is true for log of x plus 4 is equal to log of x plus the log of 4, that's actually really useful in some of our other problems. So keep that in mind, that that's true. Okay. So here we've got two natural logs adding each other. So we can say the natural log of x times by x minus 4 equals the natural log of 5x. Again, that implies that x squared minus 4x has to be equal to 5x. Well, then that would be x squared. If we minus 5x from both sides, 4x minus 5x, sorry, negative 4x minus 5x would be negative 9x equals 0. Which implies that x times x minus 9 is 0, which means that either x equals 0 and or x minus 9 equals 0, which is x equals 9. Then we have to check for extraneous solutions. So the natural log of 0, there's your extraneous solution. You can't take a natural log of 0. Let's double check the other one just to be sure. Natural log of 9 plus the natural log of 9 minus 4 would equal natural log of 5 times 9. So, natural log of 9, plus the natural log of 5 is about 3.81. And the natural log of 5 times 9 is also 3.81. Why would that be, guys? Because of the sum property. Natural log of 9 plus the natural log of 9 minus 4 is the same as natural log of 9 times 5. Hey, look at that. That just makes sense, right? Okay, good. So that one does work. That's our solution. Okay. Okay, we will talk about this one because it has the two different bases. Okay. So I want to make sure you guys know how to deal with it if you have more than one base. Okay. Okay. So what this is saying right now is that if you had this as its own little function outside of this problem, we would have log base 2 of x is equal to y. Which then implies that we have a base of 2, an exponent of y, and it equals x. Okay, now if we look at this one over here, if we had this independently, we would be saying log base 4 of 2x plus 24 would also equal y. Okay, and that would imply that we have a 4 to the power of y would be equal to 2x plus 24. Now 4 can be base changed to a 2. This could be 2 squared to the y equal to 2x plus 24. Which would be the same as 2 to the 2y equals 2x plus 24. Okay. But. We can essentially use a u substitution here. Because 2 to the y power was x. Which means if we square x, we would get 2 to the 2y. But this is 2 to the 2y. So we're going to substitute this out for an x squared. So then we get everything on one side. We try to factor. So the factors of 24 that would work here are -6 and +4. So either x equals 6 and or x equals -4. Okay, I know that this is weird. I know that this is a conceptually weird thing. Okay? We're essentially using u substitution. We're saying that u is x squared, and then u, well, no. We're saying that u equals 2 to the power of y. And therefore u squared equals 2 to the power of 2y. Okay? And we're recognizing that this is here, this is here. Okay? But remember, u and x are equal to the same thing. So that's why we can do this. We can go from here to here because this and this are equal to the same thing. Okay? Then again, we do have to check for extraneous solutions. So log base 2 of 6 would need to equal log base 4 of 12 plus 24 would be 36. Okay? So think about it this way. Oops. 2 to what power is 6? 4 to what power is 36? Well, can't you see right now that this is 2 to the 2x equals 6 squared? So aren't these both going to be true? So let's go ahead and check. Let's check in our calculator. Okay. So log of 6 divided by the log of 2. And then the log of 36 divided by the log of 4. Hey, look at that. That's the same thing. That one works just fine. That one's good. Okay, and let's check -4. And I already know this is going to be a problem because log base 2 of -4 is not real. That one's not going to work. Okay? Alrighty. I'm going to leave this one for you guys to try and do on your own. I'll post the complete answer if you get stuck. And one last thing we need to do, we just need to learn about finding inverses. So remember, an inverse is where we switch x and y. So we get x equals negative log base 6 of y plus 3 plus 2. And then we have to solve for y. So the first thing I'm going to do is minus my 2. So we get x minus 2 equals negative log base 6 of y plus 3. Then I'm going to divide out my negative here. And I'm just going to go ahead and distribute that right now. So negative x plus 2 equals log base 6 of y plus 3. Now I have to get rid of my log base 6, so I'm going to take 6 to the power of all of this and 6 to the power of all of this. So that part will cancel. And we have 6 to the negative x plus 2 equal to y plus 3. Then our last step is to subtract our 3 over. So the inverse of negative log base 6 of x plus 3 plus 2 would be y equals 6 to the negative x plus 2 power minus 3. There you go. Okay, I know that was kind of a lot. I hope that this makes sense. Please let me know what questions you guys have, and hopefully see you soon.